So we've looked at approximating the area under the curve using n rectangles and trapezoids. Just in terms of rectangles, what we do is we take an x value within a given interval, and the x value we choose can be anywhere, and we take the y value associated with that x value for each interval, interval 1, interval 2, interval k, up to interval n, and we multiply that height by the width, which we label as delta x, where delta x is the difference between the two endpoints divided n times, b minus a over n. And so to get the sum of n rectangles, which we call a Riemann sum, we take the sum of n rectangles, so as k goes from 1 to n, of length f of x sub k times delta x. Now sometimes you'll see a little star in some books beside the x. That just means that the x value that's chosen to determine the y value can be anywhere in the interval, and in fact it can be chosen differently for every interval. Okay, we're not going to get into that, but that's the notation that's often used. In terms of trapezoids, our trapezoid looks like this, remember? And the area of a trapezoid is 1/2 height times a plus b being the two parallel sides, the height being here, which is the same as delta x. So we could find the sum of n trapezoids by using this formula. Let's pull the 1/2 out front, and we're going to sum up n trapezoids. We're going to take the y value at this end and the y value at that end, f of x k plus f of x k plus 1. So that's like our a plus b times our delta x. And so in these two ways we can come up with approximations for the area under the curve. Now, as we said in the last video, if we increase the number of rectangles or trapezoids to become larger and larger, then our approximation will become closer and closer to the actual area under the curve. So that suggests that what we need to do is we need to increase the number of rectangles endlessly, which implies taking a limit. And so the area under the curve will be the limit as n goes to infinity. Now, another way to say that would be to say that delta x, our subintervals, goes to 0. If we do that limit of our Riemann sum or of our trapezoidal sum. Okay, the limit of Sn will give us the area under the curve. So we're going to go back to the example we were working on in the last video, which was approximating the area under y equals x squared between 1 and 3. We were doing approximations for that area using 4 rectangles. Now we're going to move towards finding the actual area. So the first thing we want to do is we want to find an expression for the sum of n rectangles. So our formula is as shown, and what we need to come up with here is an expression for f of x and delta x. Well, our interval this time is still a length of 2, but we're breaking it up n times. So our delta x is going to be 2 over n. Now, we're being told here to use the right endpoint to determine the height of each rectangle. So if I begin over here on the left, and remember I'm breaking this up n times, my first rectangle would be something like that. This x value, which I'll call x1, will be 1 plus 1 change in x, which is 2 over n. Okay, the second rectangle, again using the right x value to determine the height. And that x value will be 1 plus 2 jumps of delta x. Now what we need to come up with is x sub k in order to apply this formula. So we can see that on the kth rectangle we would be at the starting point and k jumps of 2 over n. One rectangle was 1 jump of 2 over n, 2 rectangles was 2 jumps of 2 over n, the kth one will be k jumps of 2 over n. Alright, so therefore f of x k will be that quantity squared, since that's the function. Alright, let's put all this together into our formula. So our Riemann sum, the sum of n rectangles, is expressed as this formula. Times delta x, which is 2 over n. Now what I need to do is I need to simplify this expression in terms of n, and then I can use that formula with different values of n to take a limit and find the actual area. Alright, we're now going to work at simplifying this formula, and that's going to involve using some of these formulas that we talked about in a previous video. We need to replace the sigma notation with the corresponding formula. So at this point, this is essentially an algebraic exercise. Okay, 2 over n is a constant, so that can come out front. I'm going to square this out. And now the sum of a sum is the sigma of each of these. I can also pull the 4 over n out at the same time as I'm rewriting this. Okay, 1 plus 1 plus 1 n times would be n. Okay, I'm replacing my formula for the sum of k, which is n times n plus 1 over 2. And my formula for k squared. Alright, and now I'm just going to simplify this. Just distributing that through, and on the top here I'm going to multiply this out, which is 2n squared plus 3n plus 1, and then I'm going to distribute the 2 through. So I'm doing a few things at a time here. 4n squared plus 6n plus 2 all over 3n. Going to get a common denominator here. This is 3n multiplied top and bottom by 3n, so that's 9n squared plus 6n plus 4n squared plus 6n plus 2. And so the sum of n rectangles is that's 13n squared times 2, 26n squared. That's 12n times 2, 24n plus 2 times 2 is 4. And so we come up with our Riemann sum, which is a formula for the sum of n rectangles. So if I had split my interval into 4 rectangles, if I substitute 4 into this formula, it will tell me the sum of those 4 rectangles. Or I could put 40 in, or 100. Okay, let's just do that. And you'll see that as we make n larger and larger, our approximation will approach the actual area. So I have my formula typed in here. It's a bit cut off, but it's all in there. Okay, and let's go over to our table. So if I had split the interval into 4, our area would have been 10.75. Now in a previous exercise you would have worked this out, and that should confirm the answer we got back then. If I did 10 rectangles, my approximation would be that, 20 rectangles. Okay, and so I can keep doing this with a larger and larger number of rectangles. And as I do that, you're noticing that the number here is getting closer and closer to some value around 8.6-ish. So instead of just approximating that with the calculator, we can actually find the area by doing the limit as n goes to infinity of our Riemann sum. And since we know how to do limits analytically, that won't be a problem. Okay? As n goes to infinity, the lower powers have less significance, so we can ignore those. And we have 26n squared over 3n squared, so the n squareds cancel out. And we then get 26 over 3, which is 8.6 repeating, which is the actual area under the curve. Alright, now as an exercise, I'm going to ask you to find the Riemann sum using the left endpoint to determine height. You're going to get a different Riemann sum. You'll get the same total area in the end when you take the limit. So I'll ask you to do that, and then we'll check it out in class. Your Riemann sum, Sn, should turn out to be 26n squared minus 24n plus 4 over 30n squared. See if you can get that, and then take the limit, and we'll discuss it in class.